recall this result that we came across in the previous vector space video. In fact, this is where the video ended. This is where means we proved this result, and although the result itself is not that much of a big deal, but we mentioned that it has very important consequences. So today in this video we are going to start with those consequences. But before we do that, let us again recall what the result actually says. The result says that if in our vector space V, finitely many vectors are given, then either these vectors are linearly independent, or of course they are linearly dependent, and in that case you will be able to find one vector among them that is a linear combination of the preceding ones, that is those vectors that appear before it in this list. Now I am noticing something which I don't remember if I have mentioned that in the previous video. I think here this condition is true. Either n is greater than 1 or n is equal to 1 and V1 is not equal to 0. Why I am saying this thing? It is because you see what we have here. We are concluding that either these vectors are linearly independent or some Vk is a linear combination of the preceding ones. If none of these conditions is true, if we don't have n greater than 1 and also we don't have this, that means n is equal to 1 and V1 is equal to 0. What will happen in this case? We can have this, right? I mean, if nothing else is given to us, we can have only 0 here. That is also finitely many vectors in our vector space. And the 0 by itself is linearly dependent. We have seen these things when we learned linear dependence independence for the first time. We saw that this singleton set consisting of only the 0 vector is linearly dependent, and in fact in any set if we have the 0 vector it becomes linearly dependent. So it is linearly dependent, that means it's not linearly independent, and also it is not a linear combination of the preceding ones because there is no preceding vector. So you can of course assume that n is greater than 1 in this theorem. That's because this other case where there is only one vector and that is non-zero, it also does occur, but it occurs less frequently than this one. Mostly you can assume n to be greater than 1. If my arguments here in this part, this aspect of this theorem is wrong, if there is something wrong, that no, in this case also the conclusion of the theorem actually is true, then please let me know. Okay, now we are going to see the important consequences of this theorem. So the first consequence is this: corollary 1. In this corollary, we again are starting with finitely many vectors. If these vectors in V have W as their linear span, and if these vectors, the first k vectors from among these vectors, are linearly independent, then one can find a subset of the original vectors of this form. Consisting of linearly independent elements whose linear span is also W. Let us see what this statement is. This part we have seen, so we can wrap this up. Loosely speaking, a finite set of vectors is either linearly independent or some vector is a linear combination of the preceding ones. So we remember this. Now in this corollary, what we are saying is this: we are given a set of vectors which is a dependent set or an independent set. We are not saying anything like that. Okay, we are just given a set of such vectors whose linear span is being considered, and that linear span we are calling W. It is now given that this subset of this original set consisting of the first k vectors is linearly independent. Then one can find a subset of this one again, of this form, where those first k vectors are there and possibly some other vectors. Such that this new set is also linearly independent, just like this one, and its linear span is still that original W. We have to show that such a set exists. Note one more thing here, that this part of the hypothesis which says that this set is linearly independent, it can change. Change means here this k can be as small as 1. In that case, we have only one vector that is linearly independent, or k can in fact be also as large as n. In that case, the original set itself is linearly independent. And in that case, where k is equal to n, these extra possible vectors are not there. Okay, that's why we are saying possibly extra vectors. And that is the case with which we are going to start the proof. So in the proof, that will take up only one line, that when k is equal to n, we are done. So before we write those things, let us see here itself, since we have written all the things here, what happens in that case. When k is equal to n, then in place of this set, we have this set itself. And in this case, this set is of this form because k is equal to n and these extra vectors are not there. Now, what are the claims about this set? This set is linearly independent, this is linearly independent in this special case. And that is just the hypothesis. And its linear span is W, which is coming from the definition of W itself. So in this case, there is nothing to prove. So let us start the proof accordingly. If the original vectors are linearly independent, then we are done. We have just seen now how we are done. If not, then weed out the first Vj that is a linear combination of the preceding ones. Now, what is this second line? In this second line, we are saying if not. That means if these are not linearly independent. Then we know from theorem 421 that some Vj among these vectors will be a linear combination of the preceding ones. So that this fact is coming from theorem 421. Although it hasn't been explicitly mentioned here, but it's coming from that theorem. And this Vj is not just any such Vj, it's the first Vj that one encounters as one goes from left to right. And that Vj, what we are doing to it, we are weeding it out, we are removing it from this set, thus reducing the number of vectors by 1. Now something can be said about this J. Since these are given to be, the first k are given to be linearly independent. j must be greater than k. That is equivalent to saying that vj which we are removing will not appear among these vectors. Why? Because if vj appears among these vectors, then vj is a linear combination of the preceding ones, and using this fact you can show that these vectors are not linearly independent, contradicting the hypothesis. You know how to show that, but still I am showing it. You see, vj is a linear combination of the preceding one. So if this is the case, then some linear combination alpha j minus 1 vj minus 1 is equal to vj. Okay. Then you will have a linear combination like this. Minus vj plus 0 vj plus 1 plus 0 vj plus 2 etc. plus 0 v k is equal to 0. And you can see that in this linear combination all the scalars are not 0. We don't really know what the alphas are, but this minus 1, the coefficient of vj is not 0. Minus 1, the additive identity of the unit element in the field is never equal to 0 in any field. So that's why this is a non-trivial linear combination, and that is equal to 0, which implies that this set is linearly dependent, contrary to the hypothesis that it is linearly independent. So that's why vj cannot appear among these first k vectors. If you are wondering what would happen if vj is equal to v1, vj will not be equal to v1. It is because you see, what is vj? Vj is a linear combination of the preceding ones. That means there are vectors before vj in this list. Okay. And what happens if j is equal to k? Fine. In that case, these things are not even there in the scene. So we don't have to consider this extra part, because minus vj itself is minus vk, and that would also contradict the hypothesis that these vectors are linearly independent. So that's why j must be greater than k. And we have removed this vj from the original set of n vectors. The resulting subset So after this first k vectors, we have vj here somewhere, and we have removed it. So we have the vector before it and after it, but not the vector itself, as n minus 1 vectors or n minus 1 elements. You may have noticed one thing. We are saying subset, but we are just simply writing a list, not enclosing the elements in the list within curly brackets. That is just writing things somewhat casually. Strictly speaking, this is not correct technically. However, you can understand what the author is trying to say. If you want, you can write, if you are writing say subset, you can write like this. Okay, so this has n minus 1 elements. The linear span of these n minus 1 elements is obviously contained in W, that is this is contained in W. You understand why? Because W is the linear span of all the V's. Whereas you have one V missing. So this set of which we are taking a linear span is itself a subset of this. So the linear span will also be in that same containing relation. Recall this result that if S is a subset of T, then the linear span of S is a subset of the linear span of T. So we are using that here. But the reverse inclusion is also true. That's the important thing to note here. However, however is not the word, but W is also contained in the first linear span, this one. How? Or let's write like this, to see that we take any element W in W, then by the definition of capital W, since it's the linear span of all the V's, small w will be a linear combination, some linear combination of those V's. We are going to show all the relevant vectors. alpha j vj vn for some scalars in the underlying field. Now, since Vj is a linear combination of the preceding vectors, we have Vj equal to Vj itself is a linear combination. Some betas will exist, some scalars for which this linear combination will be equal to Vj. Thus, if we use this expression in the original linear combination, what do we get? Alpha k vk plus alpha j minus 1 vj minus 1 plus alpha j. Now in place of vj we are going to write this beta 1 v1 etc. plus beta j minus 1 vj minus 1 plus alpha j plus 1 vj plus 1. Vn, and this belongs to, you can see that in this final form we don't have Vj but we have the other V's. So that means W is a linear combination of the other vectors V. And so W will belong to the linear span of those vectors. So capital W, our original linear span, is also contained in this one, and that's why those two things are equal. So what we have done, we have removed the vector Vj from the original set, and the resulting subset still has the same linear span W. And what is Vj? Let's also recall what Vj was. Vj is the first vector that we encounter in this list, which is a linear combination of the preceding ones. And we know that this j has to be greater than k, so that in this process of removal, the first k vectors are unchanged, they stay intact. Okay. Continuing, this weeding out process we eventually get a subset k vi1 of the original set of vectors whose linear span is W and where no vector is a linear combination of the preceding ones. How? We remove one Vj, we get a subset. The linear span does not change. Like that, we remove another Vj. Maybe after the first removal, we still encounter, if we go further down the list, we encounter the next Vj, which is a linear combination of the preceding ones. We remove that also, and we continue doing this. But at some stage, we will get to a subset like this, where no vector will be a linear combination of the preceding ones. Why? Because you see that in our process of removal, we are affecting only this part of the set, which of course has only finitely many vectors. In the extreme case where all these vectors are, each one of them is a linear combination of the preceding ones, they will be removed. So we have to remove a lot of vectors, but still it's finite. So at some stage we will run out of vectors. And in the general case where maybe not all these vectors in this part are linear combinations of the preceding ones, they will survive. But still we will run out of such vectors. In any case, we will come to a subset like this, where we don't have such vectors, which are linear combinations of the preceding ones. And keep in mind, this process of removal is not affecting W, our capital W. No matter how small we make this subset by removal of vectors, the linear span continues to be W, because it is W, that is true, we have seen once, so it will happen again and again. So that means as far as linear span goes, we are removing unnecessary vectors. So that's why the linear span is not changing. And the first k vectors, that part which itself is linearly independent, it stays intact. But then by theorem 421, the vectors in our final set are linearly independent. So once we understand how that is the case, the proof is over. Apply theorem 4 to 1 to this list of vectors. By this theorem, either these vectors are linearly independent or some vector from this list is a linear combination of the preceding ones. But we don't have such vectors which are linear combinations of the preceding ones. We have done removing all of them. So that's why by this theorem, this list must consist of linearly independent vectors. There is no other choice, and that is why we have got a linearly independent set whose span is still W, and the first part of that set, which consists of the original linearly independent vectors from the original set, stays unchanged. Okay, so that is the proof. Here the proof ends. You can probably understand why we are writing I1, I2, etc. These I1, IR, they are integers lying in this range. Since we don't exactly know, we don't really know which vectors are going to be removed, so we don't know what suffixes we will end up with. So that's why we are in general writing I1, I2, IR, and we also don't know how many of them will survive in the end. So that's why a notation like this. Note one more thing carefully. Okay, this should also be mentioned. Do you see the line here? We will eventually get a subset whose linear span is W and where no vector is a linear combination of the preceding ones. Okay. Our removal process attacked this part, right? That comes after Vk. So in this part we have removed all the vectors that are linear combinations of the preceding ones. But what about this? Can you have a vector here in this part that is a linear combination of the preceding ones? No, because these are already given to be linearly independent. So that's why, and we have already seen what happens if we consider such a Vj here. We get a contradiction. So that means what we are saying, that no vector is a linear combination of the preceding ones, means actually no vector, not just this part, the entire set. This set has that property, that no vector including this first k vectors is a linear combination of the preceding ones, and that's why we are able to say that by theorem 4 to 1 this is linearly independent subset of the original set. So now we have understood the proof in its entirety. We are saying this corollary is very important, although we can't see that importance at once. Slowly it will be apparent. Let us now see another corollary based on this one. Corollary 2. If V is a finite dimensional vector space. Then it contains a finite set of vectors of that is linearly independent. Elements whose linear span is V. Let us recall what the definition of a finite dimensional vector space was. We say that a vector space is finite dimensional if we find a finite set, a finite subset of the vector space whose linear span is equal to the vector space. If a finite set can be found in the vector space which has the power to generate the entire space in this sense, then we say that V is finite dimensional. If you recall the examples that we saw after defining vector spaces, there we encountered this space, the space of all polynomials over a field. There we saw that this space does not have finite dimensionality. Here, the space in this sense is so large that no finite set can be found in it that has the power to generate the entire space. Okay. So that is what finite dimensionality means. Now, what we are saying in this corollary is that if we have a finite dimensional vector space V, then we can find a finite set of vectors in V whose linear span is V. That of course is it comes from the definition of finite dimensionality. We don't need this result for that. However, additionally what the result says is that not just any finite set but a finite linearly independent set can be found whose linear span is V. The proof starts with a case which actually has been disregarded by Herstein. That case where V has only one vector, namely the zero vector, that is the vector space V is the zero space. For the sake of completeness and rigor, we are going to include it, and because of that we, in fact, if you recall, we slightly extended the definition of the linear span of a set S. In the text, this notion has been defined only when S is a non-empty subset of the vector space. However, we extended it to the case where S can be empty, and if you recall, we called that general linear span Li. It turned out, we have shown this, that when S is non-empty, our Li and Ls they match, they are the same thing. And when S is empty, it is this. Okay, this we know, and since we are saying these things, let us also recall what LIS is actually. By definition, Li of S is the intersection of all the subspaces of the original vector space all of which contain S as a subset. With that definition, this Li becomes our original L, ordinary L, when S is non-empty, and when S is empty we get this. Okay, so let's now start the proof. If you are wondering why Herstein has disregarded this case, it's because this case is something very trivial, and often mathematicians tend to disregard or ignore trivial cases. We should not do that ideally, but sometimes it's done if it is not too serious. We, however, are not any big mathematicians. We are just ordinary students, so we will have to go through the things systematically and as rigorously as possible. That is our aim, so that we don't make mistakes. They can disregard this type of things because they are experts and we are novices, rookies. So let us start with that case. First, assume V to be the zero space. Then V is okay. In this case, why is V finite dimensional? That also must be ascertained, because otherwise it would not be. It would not come under the cases where this theorem is, this corollary is applicable. V is finite dimensional because the linear span of the singleton set consisting of the zero vector is V, and that is a finite set. In fact, that is in this case equal to V itself. So that's why, because such a finite set exists whose linear span is V, so by definition V is finite dimensional. But we don't need, this set is not enough for our purposes. It only tells us that V is finite dimensional. We need a linearly independent set in its place, and this set is not linearly independent. It has the zero vector. Note that the empty set is a finite linearly independent subset of V such that the linear span of the empty set is equal to V. And this linear span is of course our linear span, that single case which is not covered in this text. So that means what we have done here, in this case, the linear span that we are saying is this linear span. This linear span means, what I am trying to say is that for Herstein, when he says linear span, the set of which he is taking linear span, that is by definition non-empty, although that has not been explicitly mentioned in the text, but it has to be non-empty, otherwise it doesn't make sense. However, because now we have a slightly extended notion of linear span which covers all the cases, so this linear span, this term, you can consider as the extended one. That's what I am saying. Okay, so now we have found a finite subset of V whose linear span, this linear span is V, and at the same time it is linearly independent. Okay, so this case is gone. Next, assume P to not be the zero space. It has at least one non-zero vector. Okay, since V is finite dimensional, there exists a finite set S which is a subset of V such that the linear span of S is equal to V. Okay, and because okay, now note one thing, that we are not using Li here. This L is Herstein's linear span. Why? Because if we use Li and we consider the empty set in place of S, then the linear span is only this, which is not the entire V because of this assumption. So that's why our S cannot be empty and we cannot consider the general Li. Actually here also we are considering the general Li, but S cannot be empty. That's what the point here is. S cannot be empty, so this is the original linear span and that is equal to V. S, just like S cannot be empty, S also must have at least one non-zero vector. S is different from these two sets. Because the linear span of both these sets are equal to this, which is not equal to V. So we directly write, since S must have at least one non-zero vector we can assume this, keeping in mind at the same time that S is finite. Where V1 is non-zero. Okay, so there will be at least one non-zero vector in S. How many elements S has, we don't know. S is non-empty, so at least one vector is there and at least one non-zero vector is there. So in this way of writing the set, we have chosen to put that non-zero vector first, phi1 say. Then the singleton set consisting of phi1 is linearly independent. Thus, by corollary 1, there exists a subset of S consisting of linearly independent elements whose linear span is phi. How exactly have we used corollary 1 here? Like this. Moisture is trapped in everything, that's why it's becoming so difficult to clean the board. Okay, in corollary 1 we start with a vector space phi and we have this list of vectors whose linear span is W, and it is given that the first k vectors form a linearly independent set. Then such a subset can be found which is linearly independent and whose linear span is W. That's what the corollary 1 says, right? Now, in our case, W is V itself. W is equal to V, and this thing is S. Because V is finite dimensional, we have this. L of S is V, where S is this. And what is this linearly independent part? That part now has only one vector. Do you see why this is linearly independent? It's because of this non-zero-ness. We cannot multiply this vector by a non-zero scalar to get the zero vector. That is possible only when phi1 itself is the zero vector, which it is not in this case. So that's why this is linearly independent. That is, no non-trivial linear combination of this single vector can give us zero vector. So that's why it is linearly independent. So in our particular case, k is equal to 1. So it's that extreme case. However, it does not matter what k is, we will still get a subset which looks like this, and that's why you see I have written v1 after that, maybe some other possible vectors. A subset of S, still it is a finite set consisting of linearly independent elements. This is now linearly independent and its linear span is W, which in our case is V. That means we have obtained a finite set of linearly independent vectors whose linear span is V, if V is finite dimensional. So that completes the proof of this second corollary. So although we defined finite dimensionality only in terms of linear span, only in terms of the ability to find a finite set whose linear span is the space, but we have seen that in that case not only such a set exists, but such a linearly independent set exists, and this prompts the next definition. A subset S of a vector space V is called a basis of V. If S is linearly independent and the linear span of S is equal to V. So combining this definition and corollary 2, we can now say that a finite dimensional vector space has a finite basis. This is not a definition, okay, this is a result, and that result is corollary 2. In this terminology, corollary 2 can be rephrased as this result, which we decide to call another corollary. Same thing, but written slightly differently using this notion of basis, and which is just this: if V is a finite dimensional vector space and these vectors span V, then some subset of these vectors forms or is a basis of V. That is, there exists some subset that is linearly independent and also spans V. That means it is a basis. Corollary 3 asserts that this is always the problem with while cleaning the board. If you apply too much pressure, the ink gets smeared instead of getting removed. But if you apply too less pressure, it won't go off. So there should be somewhat a sort of optimal pressure. Okay, so what does Corollary 3 assert? It asserts that a finite dimensional vector space has a basis containing only finitely many elements, or more simply, a finite dimensional vector space has a finite basis, say consisting of these vectors, these n vectors. Did we mention what space? It does not matter if the vector space is there in the background. Together with lemma, four, 2, 3. Now we are going to combine finite dimensionality and that lemma 4, 2, 3, which, if you recall, says that if you have a linearly independent set, then any vector in the linear span of that set has a unique representation as a linear combination of those vectors. That is, say, here we are saying that there is a finite basis this. No, so that means this spans the space and also these are linearly independent. Now that linear independence part, that is about lemma 4, 2, 3. So it says that in the linear span of these vectors, if you take a vector from this linear span, then of course, because it is coming from the linear span, it will be a linear combination of these vectors. Some alphas will exist in the field of scalars for which this linear combination equals V. But independence implies by lemma 4, 2, 3 that these alphas are now uniquely determined by V. For given V, once you fix V, there exist fixed alphas for which this will happen. So the alpha i's are uniquely determined by V. Now combine this fact with the fact that these vectors in fact generate the entire space. So this linear span is actually equal to the whole vector space V. Combining this with that, we get the fact that any element in V is now expressible as a linear combination of these basis vectors in a unique way. Okay. To match these abstract things with something that we already know, you think of vectors in 3 dimensions that you consider while studying mechanics. In 3 dimensions, you are already familiar with these vectors, these unit vectors. Say this is your x-axis, this is y-axis, this is z-axis. On these axes we have these unit vectors I cap, j cap and k cap. And whenever you write a vector in 3 dimensions, 3-dimensional space, you write things like this, no? 2i cap plus 3j cap plus say 4k cap. This is a linear combination of these unit vectors, and you seem to have taken this thing for granted that anything, any vector, whatever it is in 3-dimensional space, either like this or having any length whatsoever, is expressible in this manner. And that is true because these 3 vectors form a basis for the space of all vectors in 3 dimensions. That's why every vector is expressible as a linear combination of these vectors. And that too, there is that other fact also, that these vectors are not just spanning the whole space of all vectors, but they are linearly independent. So these scalars that you see actually are unique for a given vector. If you think of a vector emanating from the origin like this, for that vector there will be unique scalars that help you write the vector as a linear combination of this. And these scalars in physics are sometimes called components of the vector. We also say components, but for example, you have a vector which is representing some force which is given like this. Then the x component of the force is this, the y component is this, and the z component is this. And these components can be obtained by taking the dot product of this vector with these unit vectors, which is something we already know from mechanics or other parts of physics. To find work done, we use dot product. Now, just like the abstract notion of vector spaces arises from these concrete things, those notions of dot product and those things also have their abstract counterpart in inner product spaces. We will see those things, okay? They are coming. So we were saying that this tells us together with this tells us that any vector in the vector space means in the underlying space is, or let us write like this, has a unique representation as a linear combination of these vectors, these basis vectors. that is, let us mention this vector space, use a symbol for this, let us call it V, that is, for any V belonging to V, we have V equal to, say, we are using alpha 1, it does not really matter, but let's just write what the author has written. For some unique scalars. Now if we define a function, say from V into the space of all n tuples over the field F by mapping the vector V to the n tuple of these scalars. Is this function well defined? You see, for any vector in our space, such a representation exists. So that means for a given V, such alphas can be found, n number of alphas, not necessarily distinct, but n alphas will be found. So there is an n tuple. And because this expression is unique, the alphas are uniquely determined by V. So the image that you see here of V under the function F, that is unique. So that means the function F is well defined. Because of uniqueness of the above, representation of representation of small v, F is well defined. Also, from the definition of equality in the space Fn, when we say two such n tuples are equal, we know when their corresponding components are equal. Alpha is equal to beta I. If beta 1, beta 2 up to beta n is another n tuple which we are saying is equal to this one. From that definition of equality, it also follows that F is one-to-one, F is injective, and ontoness is almost obvious. If you choose any n tuple here in the second set, then such a linear combination exists whose F image is that n tuple. So the function F is onto. In fact, one can easily show that and F is not just one-to-one and onto, F is in fact a vector space homomorphism, that is a linear transformation. F is an isomorphism of V onto Fn. That is, V is isomorphic to Fn. Okay. So where did we start this whole thing? We started this with a finite dimensional vector space V. So finite dimensionality implies it will have a finite basis by corollary 2. So we are getting this n, this positive integer n from here, and this n is in fact the number of elements in a basis. Note that n is actually the number of elements I need ink. In a basis of V. If V should have another basis with m elements, then we similarly have V isomorphic to Fm. You see, finite dimensionality implies there is a finite basis. That's just it. So far, that is all we have been able to say. But we haven't been able to say anything about how many elements the basis will have. The only thing is that it will be finite. So if you encounter a basis which has n elements, who is stopping you as of now to have another basis with say m elements, where we don't know whether m and n are equal? But from our discussion here, we have seen that V is isomorphic to Fn as well as Fn. Hence, Fn should be isomorphic to Fn, because being isomorphic is an equivalence relation. Now, a natural question arises. What are the conditions on N and M so that Fn is isomorphic to Fm? We can guess a few things at this stage. One is that the first guess, without any specific reason, it's something that we feel should be true, is that these two vector spaces will be isomorphic only when n is equal to m. We cannot say exactly why at this stage, but we feel that it should be like that. Now, there are some justifications for this feeling. Two justification means not rigorous justifications, but again something vague to just about justify our feeling a little bit. Let us take the special case where this field F is the field of integers modulo P, where P is a prime. We know from our results on ring theory that this is a field. If P is a prime, then this system is a field. Recall that this consists of all the congruence classes modulo P. In total, there are P such congruence classes, P distinct congruence classes. Under addition modulo P and multiplication modulo P, this set forms a ring which actually becomes a field. So it is this field. Suppose we have this field in place of F. Then Fn has how many elements? Because in Fn the elements are n tuples, and in an n tuple there are n components. In place of each of such n components, we can have these p possibilities. So in total, the number of n tuples here, or the number of elements in this set, will be p to the power n. Just like that, what about this one? The number of elements here should be p to the power m. Now, isomorphism demands, note that in this case the vector spaces, these are vector spaces, no, actually have finitely many vectors, and these are the number of vectors in the respective cases. Isomorphism demands that these two sets should have the same number of elements, that is this, and which is possible if and only if n is equal to m. So our feeling that in general n should be equal to m is true in this particular case. Another case you can consider is when the field is the field of real numbers. when we are saying that Rn is isomorphic to Rm, we are saying that the n-dimensional real space, n space, is isomorphic to the m-dimensional real space, m space. And we feel in a vague geometric way that this is possible only when n is equal to m. And also from the other things that we have already seen about basis, although we have defined basis only in this video, but we have been seeing facts about basis, that is those sets that span the entire space and which are linearly independent. Those facts also indicate that any two bases in a finite dimensional vector space, they are finite, but now we are guessing that they must have the same number of elements. This actually is true, and this will give rise to the definition of dimension of a finite dimensional vector space. And the next results that come after this are going towards that direction, which we will of course not do in this video. We will do it in the next vector space video. So I am going to end the video here itself, and coming Friday we have again Galilean's algebra. Now before I end things, I want to mention something that we will get at some point, not here in algebra, but something that is somewhat analogous to the things we have seen today. I have already mentioned that three-dimensional vectors, right? Vectors in 3 dimensions and their expressibility as a linear combination of those basic vectors I cap, j cap and k cap. Such things are also there for functions. Functions also form vector spaces, and some such somewhat particularly behaving functions you already know, you may know from your study of analysis, have Fourier series expansions. That is a function which is expressible as an infinite series of some other functions. Okay, I am saying things very vaguely, which maybe if I remember correctly, this somehow involves complex exponential functions. Those complex exponential functions in this sense behave somewhat like the basic functions, I mean the basic vectors, although the entity you will have here is an infinite series and actually not a linear combination, but still it's as if your original function that you have here, whose Fourier series you are writing, is like any vector in a space of some particularly behaving function. And these basic functions, which are characters of a particular group, we will see these things, okay? They behave like the basis vectors, and the coefficients that you find in this are actually the components. It's like the space of functions that you are considering here has infinitely many mutually perpendicular axes, although it cannot be reasoned geometrically in that way, but it's analogous. Along each axis you find the component of this function, which is the shadow of this function, just like you find the component of a vector along the 3 mutually perpendicular axes by shining a light and finding the shadow, the length of the shadow. So these are somewhat like the lengths of those shadows of the function along those axes, along these characters, and these lengths are obtained by Fourier transforms. Okay, just like you have ordinary dot product, using Fourier transforms you can find these components. When in Tau's analysis 1 we study the part which involves Fourier series, there we will see these things. Anyway, so see you coming Friday with Galilean's algebra. So that's just it for tonight. If you want to say something about these things, you can write in the comment section below. And with that, I end things for tonight. So see you on Friday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.